Flying monkeys. Mic check. Flying monkeys. In this video, I'm going to cover two examples for nodal analysis. Before we do those examples, I want to remind you of the steps that we use for nodal analysis. We remember them using the acronym AS. The first A stands for Assign Node Voltages. We should include ground, but also include currents for branches and assume that the voltage at the first node, starting from the left, V1, is bigger than the voltage at the second node, V2, which is bigger than the voltage at the node V3, which is all bigger than 0 or ground. This may not be strictly true, but it allows us to direct our currents. The second A stands for Apply KCL and Ohm's Law. We're going to do so at each of the non-ground nodes. And finally, the S stands for Solve for the node voltages. After completing steps 1 and 2, I will have n equations with n unknowns, and I can solve the linear system of equations. In the first example, I have this circuit, and I would like to find the node voltages. Step 1 is to assign the node voltages. I'm going to start from the left and work my way right, and assign the leftmost node to be V1, and then the next node to be V2, and the bottom node to be ground. If I assume that V1 is bigger than V2, which is bigger than ground, then I know which direction my current will go because current wants to go from a high potential to a low potential. The next step is to apply Kirchhoff's current law and Ohm's law. Let's start at node 1. Coming into node 1, I have 3. Going out from node 1, I have I1 to 0, the current going from node 1 to ground, and I1 to 2, the current going from node 1 to 2. To apply Ohm's law here, I recall that the current through a resistor is equal to the voltage drop across that resistor, V higher minus V lower, divided by the resistance. So I1 to 0 is going to be V1 minus the lower voltage, which is 0, divided by the resistor between them, which is 1. And I1 to 2 is going to be V1 minus V2 over 2. Plugging these expressions in, I see that to simplify, I can multiply by 2. Multiplying by 2 and collecting terms together, I get 3V1 minus V2 equals to 6. This will be my first equation with two unknowns. At node 2, I see that I have 6 amps coming in, 3 amps going out, I2 to 0 going out, and I1 to 2 going in. Their sum should be equal to 0 thanks to Kirchhoff's current law. Plugging in the Ohm's law expressions, I get I2 to 0 equal to V2 minus 0 over 2, and I1 to 2 I already found to be V1 minus V2 over 2. Multiplying by 2 to simplify and collecting terms, I get a second equation, negative V1 plus 2V2 equals to 6. The third step is to solve. Let's do it algebraically by solving equation 2 for V2. V2 is equal to 3 plus V1 over 2. I'm going to plug this into equation 1. When I do so, I get 3V1 minus, in parentheses, 3 plus V1 over 2. This expression is equal to 6. Collecting terms together, I find that 2.5 V1 is equal to 9, and so V1 must be equal to 3.6 volts. To find V2, I plug that answer back into my equation above. V2 is equal to 3 plus V1 over 2, where V1 is equal to 3.6, and the result of that calculation is 4.8 volts. In this second example, I can see immediately that it's going to be slightly more complicated because instead of having 2 nodes, which are easy to solve for algebraically, I'm going to have 3 nodes that I have to care about. So in step 1, I will assign the node voltages, V1, V2, V3, and ground. Assuming that V1 is greater than V2 is greater than V3, which is greater than 0, this allows us to direct my currents. I can assign I1 to 2, I2 to 0, I2 to 3, and I1 to 3. I'll also notice that I1 to 2 is equal to Ix, which is providing a value to my dependent source on the right hand side. Step 2 is to apply. At node 1 I have 4 amps coming in, I have I1 to 2 going out, and I1 to 3 going out. Using the Ohm's law expressions, I get 4 minus V1 minus V2 over 1 minus V1 minus V3 over 2 equals to 0. Simplifying by multiplying by 2 and collecting the terms, I get 3V1 minus 2V2 minus V3 equals to 8. This will be my equation 1. I have 2 more equations to go. At node 2, I have I1 2 coming into the node, I2 0 leaving the node, and I2 3 leaving the node. Plugging in the Ohm's law expressions, I get V1 minus V2 over 1 minus V2 minus 0 over 2 minus V2 minus 3 over 4. All of these are equal to 0. Simplifying by multiplying by 4 and collecting terms together, I'll get negative 4V1 plus 7V2 minus V3 equals to 0. It would also be true to say that 4V1 minus 7V2 plus V3 equals to 0. Either is acceptable. At node 3, I have I23 coming in, negative 2Ix going out, and I13 also coming in. Now I noted earlier that Ix is equal to I 1 to 2. So plugging in the Ohm's law expressions here, I'll get V2 minus V3 over 4 minus 2 times V1 minus V2 over 1 plus V1 minus V3 over 2. All of these sum to 0. Simplifying by multiplying by 4 and collecting terms, I get that 6V1 minus 9V2 plus 3V3 equals to 0. This will be my third equation. I'll point out again that since these equate to 0, the negative equation is also true. Negative 6V1 plus 9V2 minus 3V3 equals to 0. Now, in order to complete step 3 here, to solve, we need to use a little more information. So let's focus on this little linear algebra cloud. If I have a system of equations such that a matrix A times a vector x equals to a vector b, then in order to get x, I take A inverse times b. Now let's put our equations in matrix form. The first equation is 3v1 minus 2v2 minus v3 equals to 8. So in the matrix A, I'll write 3, negative 2, negative 1. If x is equal to v1, v2, v3, then matrix multiplication yields this exact equation. Similarly, I can plug in negative 4v1 plus 7v2 minus v3 equals to 0, and 6v1 minus 9v2 plus 3v3 equals to 0. The first matrix is the matrix A. My variables I'm looking for are x, and b are the answers on the right hand side of the equal sign. And I know that A inverse times b is equal to x. Now to actually perform this inverse, I will use Python or MATLAB or a calculator. In this video I'm going to use Python. In Python, I start by importing numerical Python or NumPy as NP. I'm also going to need to use the linear algebra package, so I import numpy.linalg as LA. Then I construct my array A using np.array. Then I can construct my array B. Notice that as it stands, B is a row vector. I need to make it into a column vector, so I'm going to use the transpose command to do so. Now, using matrix multiplication, mp.matmul, I can multiply the inverse of A, which is la.inv of A, with the transposed vector B, and I can solve that to get x. Displaying x, I see that I get answers 3.2, 1.6, and negative 1.6, which is the solution to my system of equations. Collecting this together, this means that V1 is equal to 3.2 volts, V2 is 1.6 volts, and V3 is negative 1.6 volts. That's all. Thanks for watching. Many happy returns.